Hello. In this problem, we're looking at a graphing problem that involves spectroscopy. Let's first look at the question. A weak acid called HIN for an indicator absorbs greenish-yellowish light at 570 nanometers. The absorbance of this light increases as the concentration of the indicator increases, according to Beer's law, A equals epsilon BC. This also incorporates the distance the light travels through the solution, called B, the molar absorptivity, given the symbol epsilon, which is unique for a solution's absorbance at a specific wavelength. Specifically for our problem, A equals epsilon B times the concentration of our indicator. Beer's law follows the general form of a linear equation, for which the intercept B is equal to 0. If you collect the following absorbance data over a variety of concentrations of the indicator, which is typically what you may do in a lab, you will find that as you increase the concentration, the absorbance increases. So the first part we want to think about in this problem is plotting that absorbance data in this range of the indicator concentration to find out if it actually obeys Beer's law. Will it make a straight line? The second part of our question is to determine the molar absorptivity, or the epsilon value, for this indicator using our plot of the data, given that the path length is equal to 1 centimeter, which is typical for most spectroscopy experiments. The third part of our question is to determine the concentration of a solution of indicator that has a measured absorbance. So this is really useful if we have an unknown, we can find its concentration. So typically this is how Beer's law is used. So first we would go to a graphing program like Excel or Kaleidograph and make a plot of our data. So I've input that plot here. So we have our absorbance on our Y, concentration on our X, and we find that when we plot this data, we actually do get a line. So great, it's linear. We can also ask the program to give us an equation for that line, a linear least squares fit to the data. So then it'll give us this equation, y equals 7562.7x, and an r squared value, which tells us how good the data fits that particular line. So the first answer, part 1, or part A, was yes, it is linear, right? We have a good fit. The closer our r squared value is to 1, the better the data fit each other in a linear form. So we have a 0.9991 correlation, so that's a pretty good linear fit. So I wanted to translate this y equals equation into an absorbance equal, because what we really have is absorbance versus concentration. So let's put it in that same format. So we have absorbance equals 7562.7. And the units would be rise over run, so 1 over molarity, because absorbance doesn't really have units. So we have absorbance equals 7,562.7 reciprocal molar times the concentration of our indicator. In our second part of the problem, we're trying to figure out what is the molar absorptivity, or our epsilon value, right? So our epsilon value we can find from the slope of our line, right? Because the slope of our line is what's before the concentration, or epsilon times B. So given that our line is absorbance equals 7,562.7 reciprocal molar times concentration, and our slope is 7,562.7 reciprocal molar, that equals epsilon, and remember that we had a 1 centimeter path length, or B, so our molar absorptivity is, our epsilon value is 7,562.7 molar, reciprocal centimeters. In the last part of our problem, which is typical for most lab applications, is we're trying to find the concentration of an unknown, given that we have known concentrations correlating with known absorbance values at a particular wavelength. So in this question we had a 0.325 absorbance units. So if that's the absorbance measured at our 570 nanometers, we can use our equation to determine the concentration of the indicator. So since our equation is absorbance equals 7,562.7 reciprocal molar, concentration of indicator, we just input our 0.325 for absorbance and solve for the concentration of our indicator, which gives us a 4.30 times 10 to the negative fifth molar concentration. So the method we've used here for thinking about how to use information on a graph and a line is great for spectroscopy, but it also would work for other linear fits, other kinds of data. We can think about what is our x, what is our y, what does the slope mean, is there an intercept, or is it 0? So I hope you've enjoyed this, and if you have questions, please go through the indicated math modules below.